outline of this presentation. Okay, I'm going to talk about the design procedure, how we design a sequential circuit. I'm going to talk about sequence detectors. We'll see two different types, Moore versus Mealy, because we can design them differently. We are going to trace state diagrams as we have done before to verify the correctness of our design. So when we design, we have to verify the correctness. I'm going to talk about different examples, starting with sequence detector. I'll talk about sequential comparator, binary counter, up-down counter. So these are different examples that we are going to see. The design procedure is just the reverse of the analysis procedure. So in the case of analysis, the circuit is given to us and we analyze it. And the purpose is to produce the state table and the state diagram. That will be the last step. In the case of the design procedure, what is given to us is a description of the problem. So we call this the specification. Okay. So the meaning of specification, it is a description of the problem. If you have a small problem, we can describe it, for example, with one paragraph or one page. So I'm going to ask you design a sequential circuit that does this, this, this. So this is what I mean here by specification. I'm describing to you the problem. Now, once you have the specification, the first step is to obtain the state diagram of the sequential circuit. So what you have to do is that you have to think about the state diagram and draw the state diagram. So here we are designing a state diagram. Given a problem which is described, you need to obtain the state diagram. So this step involves design. Okay, so you have to discover the state diagram. So the state diagram is not really given to you. So this actually takes experience. Okay, so you have to give meanings to these states. How do I draw the state diagram? How many states? What are the transitions between these states? So these are the questions that you have to raise in order to draw the state diagram. That will be the most important step. This will be step number one, is very important. Now, once you have the state diagram, then the rest will be just automated to be easy. So what you have to do is that you have to assign binary codes to the states. And you say this is state 0, 0, this is state 0, 1, and so on. So you can actually assign to them numbers in binary. You have to decide, do I need 1 bit, 2 bits, 3 bits? How many bits do I need? So this is called actually state assignment. That's step number 2. And when you do the state assignment, you can fill a state table. If you have the state diagram, you can fill the state table. That's it. Now, the third step is that you have to select the type of flip-flops. Do I need D-type flip-flops, T-type, JK? What's the type of flip-flop do I need for this specific circuit? Now, once you have chosen the type of flip-flop, you can derive the equations. You can derive the flip-flop input equations, and then you can derive the output equations. And then you can draw the circuit diagram. So the whole purpose is to come up with a circuit diagram from a problem description. That's the design procedure. Now, once you have done this, you need one more step, which is called verification. You have to verify the correctness. So how do you verify the correctness? You can do it manually, but that might be tedious. Or you can actually use a hardware description language, and you can actually simulate. Okay, you can use hardware description language to describe your circuit, and you can simulate it, and you can verify its correctness. Before I start with an example, very briefly, let me talk about the state diagram. Already we have seen the state diagram when we analyze sequential circuits. So remember the meaning of state, it means it's an abstraction of memory. So whenever we are referring to state, we are referring to the outputs of the flip-flops. And when we draw a state diagram, we can give these states names. For example, I can say that state 0, state as 0, for example. It means that the last input is 0. We did not receive the 1, for example. S1 means the fact that we have seen the last input was a 1. S2, for example, it means that the last 2 input sequence is 1, 1. So we have seen a sequence of 2 1s. So for each state, we give a meaning to that state. This is very important when we are drawing, okay, the state diagram. Right. So let me give you an example now. Okay, I would like to show you an example about a sequence detector. So the sequence detector is a sequential circuit, and it's going to detect a specific sequence of bits in the input. So my input here, X, my input here is X, okay? Now, even though it is just one wire, one input, one bit, it's called a bit stream, because every cycle we can provide a different value of X. So X changes, okay? Cycle by cycle, we are changing the input X. So even though the input X here is just a single wire, a single input, it is a bit stream because it is changing over time. Now notice that time here is specified by the clock. Okay, so the clock here is an input to my sequential circuit because the sequence detector is a sequential circuit, and there are flip-flops inside the sequence detector. We must have a clock. So cycle by cycle, we are changing the input X. So for this reason, X is called a bit stream. It is bit serial, okay? And the output here is Z. It's also a bit stream. So cycle by cycle, we are also changing the output Z. Now the output Z indicates whether the sequence was detected or not. If the sequence was detected, then we output 1. Otherwise, we output 0. That's the output Z. So let us take a look at this specific example. I would like to design a circuit that detects the input sequence 1, 1, 1. So I would like to detect 3 ones in my input. Now, initially, when we reset the circuit, we did not detect anything. So therefore, we must start in some initial state. And this initial state is called S0. So S0 here indicates the fact that we did not detect anything yet. So we are still waiting to detect the first one. So it means that as long as the input X is 0, we remain in this initial state as 0. So I can draw it like this. This is my initial state. Sometimes we place a reset here, indicating that if I reset my circuit, we go back to state as 0. Okay, so that's my initial state, my start state. And as long as the input here is 0, then I would like to remain in the same state as 0 because we did not detect the first one yet. Like if we detect the first one, then I'm going to jump to a new state, which is called S1. So we're going to add a new state, which is called S1 if the input is 1. So the meaning here of S1, it means that we got the first one. That's the meaning of state S1. So we can give it a meaning, okay, to understand what we are trying to do in this design, okay, to think about the state diagram, we give meanings to these states. Right, so this is the meaning here of state S1. It indicates that we have detected the first one in my input sequence. I have to detect 3 ones. So far we have detected the first one. Then we can wait for the second one. Then if we get a second one, we are going to jump to state S2. It means that we have got a sequence of 2 ones, 1 followed by a 1. That's the meaning here of S2. And then if we get a third one, then we can reach a third state, which is called S3. Okay, so this is my state S3. It means that we have detected the sequence 1, 1, 1. So this state diagram is not really complete yet, but I'm just showing the thinking process, how we think about drawing the state diagram, okay, to detect the sequence 1, 1, 1. This is a very simple example about a sequential circuit, which is a sequence detector. So now what we need to do is that we need to complete the state diagram. What I'm designing here is a Moore design. A Moore means that the output depends on the present state only. So we show the output inside the state. It depends on the state only. So let me redraw, okay, what we have seen in the previous slide. State S0 is my initial state. So if you are in S0, the output will be 0. Notice that I'm showing the output inside the state. In S1, the output will also be 0. S2, the output will be 0. And only in S3, we get the output equal to 1. So now my output is 1 when you reach S3 after detecting the sequence 1, 1, 1. So you have to see 3 ones in the input to reach S3 and to get the output equal to 1. So notice that the output is shown inside the state, indicating that this is a Moore design. Okay. Now, is this state diagram complete or incomplete?
Incomplete.
Why?
Missing the 0.
Yeah, so it does not really show what happens if the input is 0 in S1, S2, or S3. Like, what shall we do if we receive a 0? Okay, if the input is 0 in S1, S2, or S3, where shall we go?
Return to S0.
Yes, we can return to S0 because the sequence was not detected. Exactly. So therefore here, what we need to do is that we need to complete the state diagram. And therefore, at each state, you have to ask yourself this question. What if my input is 0? What if my input is 1? Where do I go next? So look at all the possible inputs, not just one input. Look at all the possible inputs. So we don't really have these transitions. We have to add them into the state diagram. So we are going to add them. If you are in S1, after detecting a 1, if a 1 is followed by 0, you go back to state S0. After detecting 1 followed by a 1 and the next input is 0, you go back to state S0. And after detecting a sequence of 3 1s and the input is 0, you go back to state S0. So that's basically my state diagram after detecting a sequence of 3 1. So after detecting it, so this is basically at any state, if the input is 0, this will take you back to state S0. Okay. Is there a missing transition? So these actually are my missing transitions. Is there something missing in the state diagram? Are we complete, or there is something still which is missing? Do we have all the possible transitions?
The last one.
Sorry, can you say it again?
1 after S3.
Okay, so if you are in S3, okay, it shows that in S3, if the input, if you are in S3 and the input X, so here actually X equal to 0. So let me write here X equal to 0. This will take you back to S0. But if you are in S3 and the input X is equal to 1, where do you go? So if you have, let us say 1, followed by 1, followed by 1, that actually is my X input. Followed by a 4th one, where do you go? So here you have detected 3 1s, right? So this is actually my input X. Now my output Z is delayed by 1 cycle because this is a Moore design. So initially the output is 0 at S0. After receiving the first one, the output is also 0. After detecting the second one, the output is 0. After detecting the third one, the output is 1. Okay. Now, after detecting the 4th one, where do we go?
S3.
Why?
Still correct, or the output is 1.
Yeah, well, here what we have to ask is that it depends on the problem statement. So you have to be careful about the problem statement. If the problem statement indicates that we would like to detect 3 or more ones, then you will have a transition, okay, from S3 back to itself. So this means that we are detecting 3 or more ones. So this will detect 4 ones, 5 ones, 6 ones, any number of ones. So therefore, you can see that here the sequence can be overlapping. So these are also 3 ones, and therefore you are going to output also 1. So you make the transition from S3 back to itself, and that next cycle the output will be 1. Okay, that indicates that you have detected actually another sequence of 3 ones. So here the sequence is overlapping. On the other hand, if the sequence is not overlapping, you want to design something different. You don't really want the sequence to be overlapping. You would like to start a new sequence of 3 ones. You want the output to be 0 here, you want the output to be 0, and then you would like to output 1 after detecting a new sequence of 3 ones. Where do you go? So if I change the problem statement, okay, from overlapping to non-overlapping, detecting a sequence of 3 ones which are not overlapping, and you would like to start all over again, and the input x is equal to 1, where do you go from S3? Students?
It's 0.
Well, not really as 0, because after detecting the first, if x equal to 0, you jump back to S0. But if you detect a 1, now notice that S1 means got 1, right? So we can jump from S3 back to S1 directly rather than jumping back to itself if the sequences are not overlapping. So we don't really go back to S0. We can go to S1 directly. From S3, we can go back to S1 directly. So there is no need to go back to S0 and we repeat the sequence. So this way, we can actually have a design, okay, a state diagram that can detect non-overlapping sequences. So what we have here is that we have overlapping sequences. So this is why this is not shown here. And we have a transition from S3 back to itself. So this will give me 1, this will give me 1, and this will give me 1. So this can detect overlapping sequences. So you can see here we have 3 ones, here I have 3 ones, etc. So basically we'll continue to get the output 1, 1, 1, because we have this transition here indicating that this can detect 3 or more ones in the input sequence. If I change my problem statement, if I change my specification, then we have to change the design of the state diagram. So you have to be very careful about this. Okay, do you understand this? So it all depends on the problem. Now, this is an example of a Moore design. Notice that here the word Moore, okay? Because you see that the output depends on the state only. The output is shown inside the state. Okay? Right. So we have the state diagram. As I said, this is the most important step in the design process, is to obtain the state diagram. What is next? What shall we do next? We have the state diagram. What is the next step? What's the second step in the design procedure? Students, this is the question to you. Someone has to answer. Anyone?
We may try to implement it.
Okay, how? How do we implement the state diagram? We will do state assignment, which means that we assign a binary code. Now notice that these states are given names, S0, S1, S2, S3. I would like to give them numbers, okay? So what I would like to do is that I would like to give a binary code to each state. So this is called state assignment. Now the question is, how many bits do I need for S0, for S1, S2, and S3? And how many flip-flops do I need, okay, for the state diagram? In my sequential circuit, how many flip-flops? Can you answer this question? Anyone? How many states do you see in the state diagram? Oh, come on. 4 states. Why you are not really answering today? There are 4 states, right? S0, S1, S2, S3. If you have 4 states, how many bits do you need to represent 4 states in binary?
2.
Exactly. So we look here at log base 2 of 4, which will give me 2 bits. So if you use 2 bits, so you need actually here 2 flip-flops. If you use 2 flip-flops, 2 bits, you have 2 to the power 2 is equal to 4, right? So therefore, this is what we know, this is known as the state assignment. So what you have to do is that you have to assign a unique binary code. So look at the number of states. So if you have m is the number of states, then the minimum number of state bits will be n is equal to log base 2 of m. Now we have to take here the ceiling function. So this notation here, it means the smallest integer which is greater than or equal to x, which is the ceiling function. Now in our example, we had 4 states. So when you look at log base 2 of 4, this will give you 2. So you need actually 2. The minimum number of state bits is equal to 2 to represent 4 states. So you can actually number these states. You can give them a binary code. You can say that state S0 is represented by 0, 0. S1 will be 0, 1. S2 will be 1, 0. And S3 is equal to 1, 1. So this is the state assignment. We're assigning a unique binary code for each one of these states. And the minimum number of flip-flops is equal to 2. So I need 2 flip-flops. Notice that we have 2 bits. Each bit is stored inside a flip-flop. So we have here 2 bits. So therefore, I need 2 flip-flops. Now, sometimes you might have 5 states. Okay, for example, you might actually have 5 states in the state diagram. In this example, we have only 4. But suppose we have 5 states. If we have 5 states, then how many flip-flops do you need? And what will be n, the number of state bits? If you have 5 states, can you represent it with 2 bits? Can 2 flip-flops will be enough to represent 5 states? Yes or no?
No.
Okay, so how many bits do we need?
3.
Exactly, because if you use 2 bits, you can have at most 4 states. If you use 3 bits, then you can represent 5 states. You can go from 0 to 4. This will represent 5 states. So you need actually 3 bits. So from 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and then you have 1, 0, 0. You need 1 more state. Okay, so you need actually 1 extra binary code, okay, for this state, and you need actually 3 bits. Right, if you use 3 bits, what is the maximum number of states you can have? If you use 3 bits, 3 flip-flops, the maximum number of states that you can have. What is 2 to the power 3?
8.
Exactly 8 states. Exactly 8 states, right. Now, if you use actually 3 flip-flops, you can represent up to 8 states. If you have only 5 states, how many states are unused?
3.
Exactly. So therefore, if you use n bits, then you can have 2 to the power n at the maximum number of states that can be represented using n bits. It's 2 to the power n. But if you only have m is the number of states inside your state diagram, then 2 to the power n minus m, this will be the number of unused states. In our example, we had only 4 states and we used 2 bits. So therefore, the number of unused states actually was 0. So we had no unused states. Okay. So it's important to understand the unused states because I'm going to come back to it later and see how we can design, okay, a sequential circuit in the presence of unused states. Okay, so this is something to remember. Right now, what we have is that we have the state diagram. We can actually take the state diagram, we can put the information in a state table. So notice that we have here 4 states, S0 to S3. This is what I call my present state. Okay, my next state depends on the input x as well as the present state. So if x equal to 0, we make a jump here from S0 to S0, right? If x is equal to 1, if my input x equal to 1, then we make a jump from S0 to S1. This is shown here. Okay, this is actually my transition when x is equal to 1. I'm making a transition from S0 to S1. So you take it here actually state by state. You show all the transitions, okay, in the state table, and then you show the output z. Notice that the output z here depends on the present state only, and it's only equal to 1 if you are in state S3. Otherwise, it is 0. So this is my state table. It contains exactly the same information that exists in my state diagram. I'm putting it inside the state table. Now, we have already done the state assignment. I can replace the states. I can change their names into binary codes. So now we can do the state assignment, and I can replace, okay, S0, S1, S2, and S3. I can replace them with 2 bits. Each one is represented by a binary code, okay, from 00 to 11. Okay. So notice that here S0 is 00. This is all S0. This is S1. This is S2, and here we have S3. So we have done the state assignment and replaced the names of these states with binary codes. This is the meaning of state assignment. So now we have the state table and we have done the state assignment. What shall we do next? What is next? What should we do? What should we do next? What's the next step? What do I need at the end? Students, are you here? Look at this. What shall I do? I need a circuit for my design. I need to convert this state diagram into a circuit. How am I going to actually obtain this circuit?
With the flip-flops?
Yeah, I know that I have 2 flip-flops because actually we have used here 2 bits for the present state. So these are the flip-flops. In addition to these flip-flops, what is missing? I need the logic for my next state, and I need the logic for my output. So how am I going to obtain this logic? I need to produce my next state and my output. I need the equations, right? I need the equations for my next state. How did we go from here to here or from here to here? I need equations. I need the equation for the output. The equation for the output is so simple because the output here z is equal to 1 only when the present state is 1, 1. So that actually is just an AND gate. Okay, so that will be very simple and very easy to implement. But in the case of the next state, we also need equations to produce the next state. So now this is the structure, okay, of a Moore sequence detector. So we have here 2 D flip-flops. You can actually have more, but in our example, we had only 2. So these are 2 flip-flops. We're going to use the D type. These are the simplest to use. So in our example, we are going to restrict it to only D type flip-flops. We can also use the T type or JK. We can also do that in design. So we have 2 flip-flops. So what is missing is this next state logic. So what is this next state logic here? And what is the output logic? The output logic is going to produce the output Z based on the present state. So the current state here is the present state, which is shown here in this column. So the present state is the output. This is the output of the flip-flops. So I can call them, if I'm using 2 flip-flops, flip-flop 1 and flip-flop 0, I can call this Q1 and I can call it here Q0. So these are the outputs of the flip-flops. So notice that here, the current state, these are the outputs. So we have 2 flip-flops. So here we have Q1 and here we have Q0. These are the outputs. Okay, so what I need is that I need to determine the next state. So I need to determine here the D1 and the D0. These are the inputs to the flip-flops. So I need to obtain this next state logic that was going to produce D1 and D0 based on the current state and the input X. In the case of the output Z, the output depends only on Q1 and the Q0. That's basically is the output. So what we need is that we need minimal expressions for the next state logic and the output logic. How can you tell me how to obtain these minimal expressions for the next state logic and the output logic? Do you know a method to obtain the minimal expressions for the next state logic and the output logic? How do you do it?
Carnot maps.
Yes, Carnot maps. The same way. You see, the next state logic and the output logic are just combinational circuits. So basically, if you know, okay, if you have the, so you can actually obtain the equations from the state table. You have the state table, which is basically the truth table, okay, for the next state logic and for the output logic. So we can just simply use Carnot maps, exactly, Carnot maps. So here we have the state table, which is actually a copy of what we have seen from the previous slide. Remember that the present state, these are the outputs. So the outputs, we call them a Q. So we have two outputs, Q1 and Q0. The next state here, I mean the D inputs, D1 and D0. So we have here two flip-flops. So let me write here D1 and D0, okay, when X equal to 0. And this is D1 and D0, okay, when X is equal to 1. So what I need is that I need an equation for D1 and I need an equation for D0. So I need two Carnot maps, one for D1 and one for D0. So notice that here Q1, so you can see that here, this is actually the column for D1. And this is the column for D1. So we're going to copy these columns here. When X is equal to 1, so when X equal to 0, this is X equal to 0, and this is X equal to 1. So we are going to copy, this is when X equal to 1. But you have to be very careful about the Carnot map, is that you can see that the 1, 1 appears before 1, 0, whereas here 1, 1 appears after 1, 0. So you have to copy this row before the 1, 0. Okay, so you have to make sure that when you copy the bits into the Carnot map, you copy them properly. So here we have 4 zeros. You can see these actually are 4 zeros. These two are identical here. Okay, so their order does not really matter because they are identical. The same thing, these actually are 0, 3, 1s. Basically, it's a copy. And therefore, notice that these two are the same. So we have the Carnot maps for D1 and for D0. Next, what we need is that we need to obtain the equations. Because we have the Carnot maps, we can easily obtain the equations. So we can obtain the equation here for D1, and this is the equation for D0. So I can write it here. This is D1 equal to, and this is D0 is equal to. Okay, so these are my equations. These are my next state equations. Now for the output Z, the output is so simple because the output does not depend on the input X. It all depends on the present state. It depends on the Q1 and the Q0. It's only one in one case when you have Q1 and the Q0 are both 1 and 1. So I can just implement it using an AND gate. So we can write the expressions like this. The output Z is equal to Q1 and Q0. And this is obtained directly, okay, from the state table or from the state diagram. You can obtain the equation here for the output Z. So we have the equations. Now, once we have the equations, we can easily draw the circuit diagram. That's what we are after. So when we would like to design, I would like to obtain the equations and the state diagram, and then we are done. So notice that I have two flip-flops. So these are D-type flip-flops. The inputs are D1 and D0. The outputs are Q1 and the Q0. Notice that they are connected, both of them, to the same clock. So they change at the same edge of the clock. I'm using here bubbles at the inputs of the clock. This indicates that we are using the negative edge of the clock. So therefore, we change these two flip-flops at the falling edge of the clock. If we did not have these bubbles, then they will change at the rising edge. So we can actually have different types of flip-flops, depending, of course, how the flip-flops are implemented. You can use either the falling edge or the rising edge, depending, of course, on the circuit designer, okay, when he would like to change, okay, the state of these flip-flops. So the state of the flip-flops, this is the present state, which appears at the output, the Q1 and the Q0. This is the present state. The next state appears at the inputs, D1 and D0. This is the next state. So notice that this is the input X, right? This is here is what? This input here is what? It's Q0, right? This is also the input X, and this is Q1. You can see this is actually the Q1, correct? And this is the input X, and this is actually Q0 prime. I don't even need an inverter because we can take the output of Q0 prime and you can connect it back in the case of D0. So notice that here Q1 and X is the same term that appears in D1 and D0. So that's actually here Q1 and X. So this gate is shared by D1 and D0. So basically we have the equation for D1, we have the equation for D0. So this is my next state logic. This is what I mean here by next state logic. And the output logic is so simple. That's my equation for Z. It is just an AND gate. And notice that Z does not depend on the input X. So this is my output logic. So you can see that my sequential circuit consists of two D-type flip-flops, next state logic, the output logic. We're able to obtain the equations using the Carnot map technique. So these are the steps. That's it. That's how we design a sequential circuit. طيب.
So, Doctor, it is overall it is similar to what we've been doing in the combinational circuits.
Well,
like
the next,
obtain.
So the next state logic is nothing but combinational. But what we have done is that we have added the flip-flops inside the circuit, and we're able to figure out how many flip-flops we need depending on the number of states that we have in the state diagram. And we recognize that the present state here, which is our Q1 and the Q0, are fed back and they become inputs to the next state logic, whereas the output of the next state logic is the next state, which are D1 and D0, which are the equations at the inputs of these flip-flops. Yes. So if you actually can see this, then you understand how these sequential circuits are designed. And another thing is that the output, if the output depends only on the present state, which is Q1 and the Q0, and does not depend on the input X, then this means that we have a Moore sequential circuit. It's not Mealy, it is Moore. I'm going to show you next how we can design a Mealy sequence detector. Any other comment about this, or observation or question? So we have seen an example about a Moore sequence detector. Let us repeat the same example, but let us design a Mealy sequence detector. So I would like to detect the sequence which is 111. Again, this is the same sequence, but I would like to design it differently using a Mealy. Okay, so the state diagram is going to be Mealy, and the sequential circuit is going to be Mealy. So we're going to start initially with state as 0. Now notice that as long as my input is 0, we're going to remain in the same state and the output will be 0. Now notice the difference here is that I'm going to show the output on the arc. Okay, it's not inside the state. So you can see that the output depends not only on the state, but also on the input. So it depends on the input as well as on the state. So the state here is as 0. The input here is X equal to 0. And slash the output Z is equal to 0. Now, after detecting the first one, as before, we are going to jump to state S1, indicating that we have detected the first one. And the output is still 0. After seeing the second one, we are going to detect, we are going to move, transition to state S2. So state S2 indicates that we have detected the input sequence 1, 1. Now, my question is to you, if you are in S2 and you detect a third one, where do you go? This is my question to you. So now you are in S2, it means that you have detected the sequence 1, 1. And now you would like to detect the third one. So if the input is equal to 1 in S2, where do you go? This is my question to you. Well, do we really need S3 as we have done in the case of Moore?
Maybe no, because the output will be shown
on the arc. So therefore, we can make a transition, okay, from, let me just repeat the question again. I would like to complete the Smeary state diagram. So now at S2, if the next input is 1, I'm going to show the output equal to 1 on the arc. So there is no need to make a transition to a new state because the output is not to be shown inside the state, it is shown on the arc. So I can show it like this. I can say that if the input is equal to 1, that will be my third one here. Then the output will be 1, and it is shown on the arc without the need to add an extra state. So there is no need for state S3 because the output is shown on the arc. This is really a difference between Mealy and Moore. So in the case of a Mealy, you can really reduce the number of states. You can actually have less states than in the case of a Moore, which is really good. Now, if the inputs are zeros, we can just go back here. We need to complete the state diagram. So for example, in S1 or in S2, if the input is 0, you can just jump back to state S0. Okay. So notice that here we have reduced the number of states. We had 4 states in the case of the Moore design. Now we have only 3 states in the case of the Mealy state diagram. Okay, so that's the same. It's going to detect the same sequence 1, 1, 1, 1, but this is a Mealy machine, not a Moore machine, that uses only 3 states versus 4 states. Right. Let me ask you this question. How many flip-flops do you need to implement the state diagram? How many flip-flops do you need?
2.
2. Why not 1? Can we implement it with only 1 flip-flop?
We have 3 states.
Yeah.
Because we have what?
3 states.
Exactly. And because with 3 states, can you implement 3 possible combinations with only 1 bit?
No.
So if you use only 1 flip-flop, it can be either 0 or 1. So it can only implement 2 states. So you must use 2 flip-flops. Now, if you use 2 flip-flops, how many possible combinations can you have? Or how many possible states can you have if you use 2 flip-flops?
4 states.
Yes. So how many states are unused?
1.
Exactly. It will be 4 minus 3 to be 1. So you see that these are the questions that you have to ask yourself. Okay. So you must actually ask yourself these questions. So this is known as state assignment. So you have to ask yourself, how many state bits? What I mean here by state bits, I mean how many flip-flops do I need? Because each flip-flop can store 1 bit. So the minimum number of flip-flops or state bits will be equal to 2. Why 2? Because I need to implement 3 states. So I can actually assign binary codes. I can say that S0 is 0, 0, S1 is 0, 1, and S2 is equal to 1, 0. Notice that state 1, 1 is unused. So we have 1 state which is unused. And now I can draw the state table and I can replace, okay, S0, S1, and S2, I can replace them with binary codes, 0, 0, 0, 1, and 1, 0, okay? And notice that here I'm showing the next state and I'm showing the output 0. The next state is shown when x equal to 0 and when x is equal to 1. This is my next state when x equal to 0. And this is when my next state when x is equal to 1, according to this state diagram. So just take the information which is shown in the state diagram and put it in the state table. Now notice that the output z depends on the input x. So this is the output Z when X equal to 0, and this is the output Z when X is equal to 1. So notice that here the output Z is equal to 1 when you are in state S2 and the input X is equal to 1. Notice that if you are in state S2 and the input X is equal to 0, you get the output equal to 0. So notice that here it is 0, here it is 1. Okay? So we have the state assignment, we have the state table. What is next? What shall we do next?
The circuit.
Yes, but before you draw the circuit, what do you need?
Equations.
Equations.
Yeah, the equations.
Exactly. How are we going to obtain these equations?
Carnot map. From
Carnot map, yeah.
maps. Perfect, perfect. So we need the Carnot maps. Now, in the case of Carnot map, we have to show the present state. So remember that the present state are the outputs of these flip-flops. So I'm going to write here Q1 and the Q0, right? This is the present state. So this is the Q1 and the Q0. And this is my input X. So now D1 here, the next state here, what I mean by next state, I mean D1 and D0, because these are the inputs to the flip-flops. So the inputs of the flip-flops are my next state, okay? These actually are my inputs. So notice that this is D1 here, and this is D1, and the other column is D0. So we need two Carnot maps. I need one Carnot map for D1, and I need a second Carnot map for D0, and I need a third Carnot map for my output Z, because we have three equations that we need to obtain, okay? Fine. Now, in the case of the present state, it can be anywhere from 0, 0 to 1, 1. Now, notice that 1, 1 is not a used state. It is unused. Now, because it is unused, we are not really expected to reach the state. There is no transition to the state, okay, in the state diagram. So therefore, we show here don't cares, okay? So in state 1, 1, it does not really matter, okay, because you are not really supposed to reach this state. It is an unused state. So therefore, whether the input X equal to 0 or whether the input X is equal to 1, the next state is a don't care. You don't really care, okay, what will be the next state. And you don't really care about the output X. So I'm putting don't cares. And the reason why I'm putting don't cares is that we can use these don't cares to simplify the equations. So notice that here for X is equal, so for Q1, Q0 equal to 1, 1, here we have don't cares, here we have don't cares, here we have don't cares for the output Z. The rest, we just fill it. So notice that here we have 0, 0, 0. This is actually obtained from this column. Here we have 0, 1, 1. Notice that this is 0, 1, 1. Notice that 1, 0 appears after 1, 1 in the Carnot map. Be careful about this, because you can easily make a mistake. If you put 1, 0 before 1, 1, you will get the wrong equations. So make sure that you write 1, 1. Row 1, 1 has to appear before row 1, 0 in the Carnot map when you are simplifying and obtaining the equations. Right. So based on these Carnot maps, we can obtain the equation for D1, we can obtain the equation for D0, and we can obtain the equation for the output Z. So this is D1 equal to this equation. This is D0 equal to this equation, and this is the output Z equal to this equation. So we have the equations at the inputs of the flip-flops. This is my next state equations. And we have the output equation for Z. Notice that the output equation depends on X. There is X here because this is a Mealy a sequential circuit. So you can see that the output depends not only on the present state, but also it depends on the input X. I have the equations. I can now draw the circuit diagram because we have the equations. So notice that this is here is D1. Notice that we have two flip-flops. This is flip-flop 1, this is flip-flop 0. So this is D1, this is Q1. Here we have a Q0. And we have here the equation for D1 and for D0. This is my next state logic. So my next state logic describes the logic for D1 and for D0. And we have the output logic. This is for the output Z. And notice that the output Z depends on the input X because this is a mealy, okay, sequence detector. So this is basically design. We start from the state diagram. We start from the problem statement into state diagram. We do the state assignment. We ask ourselves, how many flip-flops do I need? How do I assign? How do I assign binary codes, okay, to these states? How do I, once we have the state table, we have done the state assignment, then we can go into, okay, sometimes we have unused states, so we can put the next state and the output is a don't care because the state is unused. And then we can use these don't cares to simplify the equations. And then we can use the Carnot map to obtain the next state and the output logic equation. And once we have the equations, we can draw the circuit diagram. And we are done. In fact, we are not really done yet because what we have to do is that we have one last step, which is verification. I have to ensure that this circuit is going to work properly. Okay, because sometimes I can easily make a mistake and therefore you might not even produce, okay, the correct output. So you have to detect that basically the transitions between the states is done properly. You have to detect that your output is correct. So this step, which is called verification, is very important. So let me stop here. Okay, next time I'll talk about this verification step. I will show you more examples. So today we have seen mealy versus Moore sequence detector. We have found that in the case of mealy, we can actually have less states. Okay, so notice that this is just a comparison of the two state diagrams that we have seen for mealy and for Moore. And in general, Moore can have more states than the mealy, because in the case of the Moore, the output is shown inside the state and it depends on the state only. Whereas in the case of the mealy, the output is shown on the arc. So it depends on the present state as well as on the input. The drawback of mealy is that you might actually get the glitches. This is actually when you would like to simulate and look at the waveforms, you might actually see glitches in the case of the mealy sequence detector, but these glitches will not really appear in the case of Moore. So this is done when you would like to verify these circuits. So I'll talk about verification, inshallah, next time. And I will show you more examples, inshallah.